Hello everyone, my name is Adit. Today I am here to introduce our project Energy Efficient CPU Scheduling Algorithm. The main aim of the project is to design a CPU scheduling method that saves energy while maintaining good system performance. In modern devices such as laptops, smartphones, tablets, and embedded systems, the CPU works continuously to execute multiple tasks. Because of this, it consumes a large amount of power and also generates heat. Our problem statement is to develop a scheduling algorithm that reduces CPU energy consumption without affecting speed, response time, and overall performance. To solve this problem, our project uses two important techniques. First one is DVFS, which stands for Dynamic Voltage and Frequency Scaling. This technique adjusts the CPU speed and voltage according to the workload. When the workload is low, power usage is reduced, and when the workload is high, performance is increased. The second technique is thermal aware scheduling, which helps manage CPU temperature by distributing tasks properly. This prevents overheating and improves the system stability. This project is useful because it can improve battery life, reduce heating generation, and lower electricity consumption, and increase the device efficiency. Now, I would like to invite my teammates to explain the working, implementation, and features of the project in detail. Thank you.
Hey everyone, I'm Lalit. Today I'm presenting EATS Energy Aware Thermal CPU Scheduler, a project that solves one of the biggest challenges in mobile embedded systems. How do you get a great CPU performance without draining your battery or overheating your device? We have a solution for that. That is EATS. Let me walk you through the compute simulator. Let's see how the simulator works. Standard schedulers like round robin treat every task the same. They run they run the CPU at full power regardless of actual need. That means unnecessary heat, wasted energy, and shorter battery life. It fixes this issue using two techniques. DVFS scales voltage and frequency based on actual workload. Thermal aware scheduling monitors CPU temperature in real time. Together, they give up to 50% of energy savings with zero compromise on critical deadlines. Here is the control panel. At top, you can see the scheduler, which consists of performance first, which runs the tasks at full maximum at its maximum speed, and round robin, which is a traditional technique. And each are proposed technique. And you can see the seed and also tasks, like how many tasks should be generated and the speed of the simulation. Here you can see start button, pause button, and reset, which stimulates the flow of the simulation. And also you can see the energy consume here. It shows the energy consumption in joules and the die temperature, the CPU temperature and CPU utilization, and also the tasks completed, and also deadline misses, and current power, how much power does the CPU used in watts. And also here comes the CPU. If we start the task, and we can see the C0 is working at its full power, and C1, C2, C3 are progressively at sleep mode. Here it's the frequency of the CPU of the task at which it's simulating. And here it shows the die temperature, how much temperature the CPU is currently running at. And we have the DVFS modes: ultra low power mode, balanced mode, and maximum mode. And we can see the cumulative energy, which is measured in joules. And you can see if we use eats the energy, it's less than 8 joules, and the CPU temperature is almost less than 35 joules, 36.2, which are almost less than 75 degrees Celsius. And also you can see DVFS frequency and active cores, which are actively used when needed and not used when not needed. And you can see the CPU utilization is much more less. And also you can see the instantaneous power, which is also used when necessarily needed and not used when not needed. And if we compare them with round robin and performance first, you can see the eats, which is our technique. It's consuming more less than, it's consuming only 9.9 joules, which round robin consuming round robin consuming 7.5 joules, that is 31.9 joules, and it's consuming only 6.8 joules, and performance first consuming 48.32 joules. And coming to temperature comparison, the it's consuming only 36.227 joules, and round robin taking 40.9 degrees Celsius, and performance first taking 43 degrees Celsius. And the total energy consumed, you can see the it's only taking 6.93 joules, where performance first is taking 48.64 joules, which is way use. And also round robin is taking 32 joules, 32.59 joules, which is also high. And you can see in missed deadlines, it's having 5 missed deadlines, but in performance first it's having zero missed deadlines, and also round robin also having zero missed deadlines. It's you can see it's 6.93 joules, and peak temperature is 36.2 degrees Celsius, and completed out of 19 by 20 tasks, and missed 5 deadlines, which is 85.8% versus performance first. And 48.6 performance first takes 48.64 joules, and temperature is 43.9 degrees Celsius, and completed 20 by 20 tasks, and missed 0 deadlines, which is baseline. And also round robin, which is taking 32.59 joules, and peak temperature is 40.9 degrees Celsius, and completed 20 by 20 tasks, and missed 0 deadlines. And DVFS control. The four pillars how it works on is DVFS control dynamically adjusts CPU voltage and frequency. Power scales as P equals capacitance into voltage square into frequency. This is the basic principle in which the frequency works on. So reducing voltage by 40% cuts the power by 64%, approximately 64%. Monitor dice temperature using a RC thermal model, soft throttles at 75 degrees Celsius and forces minimum frequency at 90 degrees Celsius. Critical tasks get highest priority with EDF ordering. Background tasks run at minimum power when no deadlines are urgent. The core management activates only the cores needed for current workload and reducing static leakage power by up to 75% when idle. So that's heats. So that's heats. Smarter CPU scheduling through DVFS and thermal awareness built for mobile, IoT and embedded devices where every milliwatt matters. Thanks for watching.
In conclusion, our project demonstrates that CPU scheduling can be improved not only for better performance but also for higher energy efficiency. By using advanced techniques like DVFS and thermal aware scheduling, the system can adjust CPU power according to workload and manage temperature effectively. This helps in reducing unnecessary energy consumption and preventing overheating. The project is highly useful for laptops, smartphones, tablets, servers, and embedded systems where battery backup, cooling, and performance are very important. It can also help industries and data centers reduce electricity cost on a large scale. Overall, our project provides a smart, practical, and eco-friendly solution for modern computing systems by making them faster, more reliable, and energy saving. Thank you.